Well, good afternoon, everybody. My name is Jamie Teherani, and I'm a fifth-year graduate student here at MIT. Maybe this is actually my sixth year. You try not to count too detailed when you're here for a while. But what that means is I'm getting my doctorate degree here, and so I'm getting a doctorate in electrical engineering, and my specialty is in semiconductor physics. So that's what we'll be talking about today: semiconductors. I thought of this kind of novel. I learned it's called alliteration, so I'm using three S's, and it's semiconductors, switches, and scaling. These are the things we'll talk about today. But before I get into that, I want to talk a little bit about education. I know a lot of you are in high school, and probably the first program is thinking about college and thinking about what you're going to major in, what schools you're going to apply to. Well, that's great, because college is a lot of fun, and anybody deciding not to do college, I think, is just deciding against a lot of fun in their life. But after college, if you didn't get enough fun, you can continue. And so that's what graduate school is. It's a more advanced study after college. And there's some secrets about graduate school that I think are not widespread and aren't public knowledge. They're not intentionally secrets, it's just sometimes engineers don't make the best advertisements for the wonderful things they do. Engineers and scientists, that is. So if you decide to pursue advanced studies or graduate school, you can get your master's or doctorate. And you can get it, of course, in a wide range of areas, but I'll just talk about engineering and science today. But if you decide to get an advanced degree in engineering and science, one of the things that they don't tell you is many cases they pay for your education in graduate school. So as long as you're a reasonable student doing well in undergraduate, if you decide to get an advanced degree, your education will be paid for. Not only will your education be paid for in many of the cases, they'll give you a stipend. So here as a student, I get a stipend, a monthly allowance that I live off of. So I'm not here on loans, this is my job, and I'm getting an education while I'm doing it as well. And so one of the things I want to do after I graduate is I want to be a professor. And so I think of graduate school as a really intense and probably the best internship that you're going to get in your life, because not only are the professors trying to get good research out of you, but they're trying to develop you as a person and as a future contributor to the field. So now, the reason why I'm pushing y'all for graduate school, I know you might say, oh, that's really far in the future, is because really a lot of everything's being specialized these days, right? Everything is more complicated than the next. You can't design a wheel and be proud of it unless it's like some really incredible wheel. But I guess I always think about the stagecoach. It might be weird to think about, but if you're back in kind of the pioneer times and you have a stagecoach or something, somebody could possibly make every part of the stagecoach themselves, right? Okay, like you can make a wheel, maybe you don't have the best tools, but you can make the wheel, you could fix it yourself, you know, if maybe the axle comes off, okay, maybe there's some specialized components there, but you could really fix it all yourself. Now imagine trying to fix a car yourself. Well, you might be able to do some things, but really everything has gone to such a degree of specialization that to really master anything, it requires so much education in almost everything we do, from making a projector or making a cell phone to very simple things like really mastering like high-strength steel or something like this. There's a lot of specializations, and so grad school takes your general undergraduate degree and it builds upon it. And the reason we need that is we need, in America, in the whole world, what's really allowed our modern day life possible is these advances in technology, and more specifically, advances in science and technology. And the biggest thing that we'll talk about here is semiconductors and integrated circuits, right? That's allowed your cell phones to happen. It's made your TVs ultra thin and ultra big. It's made almost everything that you look at in the world today that we use readily. It enabled this, and it enabled the future economy. So the advanced degrees not only enable you to do well in life, but it allows you to give let me say this well. It enables you to really master a specialty and really push this world forward. It really is, everybody has a part to play, but I really feel strongly that scientists and engineers really make the future happen, and they really move society forward. Otherwise, we'd be where we were in the 1900s, doing a lot of things manually, and life would be a lot tougher. So with that said, in the future you can do it. But the first thing I'll talk about is semiconductors. So semiconductors, that's a big word. Maybe you saw some today in these little lab experiences, but does anybody have any ideas of what semiconductor means to them, or what the word might mean, or examples of them, anything? Yeah?
I don't have an example, but semiconductor is like, it doesn't fully conduct electricity. It doesn't, like, electricity isn't all the way through it. It kind of resists it and lowers it.
Yeah, wonderful. So that's exactly what I was going to say. The semi and semiconductor means, the technical word is kind of conductor. So semiconductors are kind of conducting, and what that means is it's not all the way to conductor, which some typical examples of conductors are metals, and it's not all the way to insulators. My favorite insulator is the styrofoam cup. Really insulates not only heat, but it insulates electricity flow as well. And the reason for that is because electrons carry both electricity and heat. And so things that typically are electrical insulators are at the same time heat insulators as well, and same with conductors. So we have insulators and conductors. We have semiconductors fitting kind of in between. Now what's neat about semiconductors is that we're able to change the conductivity by orders of magnitude, so by powers of 10. So by about 10 to the 10. So that means if one state it's conducting at some value of 1, we can make it conduct from 1 to 10 to a 1 with 10 zeros after it. So that's a big range that we can change this. And we say, okay, well, what's the big deal? Okay, we're just use an insulator when you want to insulate. Use a conductor when you want to conducting. Well, since we can tune that, we can make a really useful switch out. But before I talk a lot about switches, I want to just show you some examples of some semiconductors. So this is a silicon wafer right here. This is a patterned wafer. It has some metal on top. But the base of it is, the bulk of it is single crystal silicon. So this is a silicon crystal. So it's a crystal just the same as a diamond is a crystal. In fact, they're in the same column of the periodic table, column 4. And so silicon is right below carbon in that case. And it is a single crystal, exactly the same as diamond, except it's a different atom, so it has different properties than diamond. But it's single crystal means that it's all the atoms are arranged perfectly with each other. And this gives it some nice uniform properties. If they're not all arranged perfectly, then maybe some parts behave differently than other parts of the material. So we take this single crystal, and this is a single crystal of silicon. And I won't get too far ahead of myself, but I wanted to show you some other examples of semiconductors. I'm sure y'all could think of a lot more than I can, but we have a laser pointer and LEDs. These are all semiconductor materials. Different materials than silicon, but nonetheless semiconductors, meaning they have this property where we can change the conductivity. And that allows us to do some neat electrical things and optical things with them. So, and of course they're in our cell phones, they're in our computers. They're in a lot of lights now because they're the controllers on the light circuits. So they control the power going through the light so that it's at the right brightness and things like that. So I mentioned that semiconductors can be used as switches. Now, that sounds a switch sounds a little bit boring to me. Like, what can a switch do that's really useful, right? We have switches all around us, and we don't get too excited about them, right? don't switch a light switch. Well, I get excited when I switch lights. I feel a little bit like God when I do it. You have to listen to me, lights. And then, and then the light burns out and God's like, but as it turns out, if you connect a bunch of switches together, so let's say I connect the outputs of some switches, just picture wall switches right now. So they have electrical wires on the inside. But if I connect the outputs of some of the switches to the inputs of the others, and I make this big network in a certain pattern, I can do logic with it. I can do Boolean algebra. And so what that means in a fancy way is saying I can do math with it. And so if I build a network of maybe around 1,000 connected in certain configurations, I can do some useful math. I might be able to add a couple of numbers together or something like this. And so that's where it starts being useful. Okay, now I can make these switches, and now I can do something that might actually help me a little bit, right? I'm not sure how it is in your math classes, but do they ever take away calculators from you? Sometimes.
Yeah.
Sometimes like you need to learn these. Well, imagine you're trying to work on some really advanced problem now, and the thing that's slowing you down is not being able to calculate things fast enough. Imagine trying to draw this complicated function, and you have to calculate each point individually. Well, in fact, they used to have people that were like the computation room, and so you give them your problem, and they would do the computations for you, because it would take a long time, especially if you're trying to evaluate these really difficult functions. And so the calculator, although it seems rather boring nowadays, was a really big, that's a big tool if you don't have any calculators. Having a calculator is a really useful tool. And so that's one of the first things that semiconductors really came into and made a really useful product. You do math really quickly. Just like we carry our cell phones around, it's a tool we use. It helps speed up maybe some communications and things like that rather than running every place to talk to everybody. The calculator did that in the past. Now, so I said you can take these switches and you can connect them all together in a network. Well, let me show you an example. So this right here, this is a transistor. This is what's called a discrete transistor, meaning it's separate. It's not integrated with any other circuit. And this is just an LED. And so if I change, you notice the transistor here has 1, 2, and in the middle it has a third terminal. That's the gate. That's kind of the switch on the light. And that controls whether current flows through the other 2 terminals. So this middle terminal is basically the light switch. So if I change the voltage on the light switch, lo and behold, I can turn the light on and off, right? Okay, well this is starting to be kind of neat, right? I can make a light turn on and off, and we already discussed how that makes me excited. But if they're single like that, and I told you maybe a simple math circuit takes around 1,000 transistors, it creates a problem, because now I want a calculator that does twice as much. So now I have to put 2,000 of these, and probably it might be around 2 times more expensive if I have to put all these components in a special order and things like that. So that brought up this new idea called integrated circuits. What if instead of making them discrete or single components, what if we can make them all at the same time? And so that's what integrated circuits allow. And so to do that, we use a reverse kind of photographic process. And so the fancy name for it is called photolithography, but it uses the same principles that camera film uses. So who here has used a film camera? Okay. So about half, or you think more than half? I'm curious. About half? You said, is that what, more than half, okay. But maybe some people have. Well, so film, you have to be very careful with exposing it to light, right? If you take it out of the camera, you gotta roll it up. Because when the film, it's a chemical, the film has chemicals in it, When you expose it to light, a chemical change happens. And now the film isn't the same in the part that's exposed to light as the part that was covered from light. And so the same thing can be used to pattern these wafers. So we take a wafer like this, and it comes out very uniform. There's nothing on it. And we coat it with this photosensitive material. Think of it like this camera film, but it's sensitive to light. And then we have a mask that we put over it, that we've designed the pattern on, that we want to pattern this. So let's say we want to make a bunch of transistors. Well, we have to put the pattern into the wafer. And so we do that by etching and all these other techniques. So we coat it with this photosensitive material, and then we shine light on it. And that causes the areas that were exposed to be chemically different than the areas that weren't. And then we expose it to some chemical and wash away the part, for instance, that wasn't exposed. So now we have a pattern left on of this photosensitive material. And now we can do some process. So for instance, we can dip it in acid. And the parts that are covered by the photo material, we call it photoresist, the parts that are protected, and the other parts can be etched. And so now we can start to pattern our features into it. So you can think, okay, well maybe we make the shape of it, and then we put metal in certain places to control it. And so we do that several times. And so we might put metal down all the way across it, and then just cover up the parts we want the metal lines to be, and then etch the rest. And so we keep doing this, and we can make really complicated circuits. And so that's what you're seeing here. You're seeing multiple steps. Part of the colors you see are because it's reflecting light in kind of like a prism way. So it's giving you this rainbow. But this has multiple layers of some layers have been etched, some layers have been impurities have been intentionally put in some areas, and then metal was put over and patterned. So the areas that look metallic are indeed metallic, and the areas that don't look metallic don't have metal in it. And so if we had a microscope, we could bring probes down and test some features of this chip. But that enabled something really great, because if we make all the transistors at once, if we add one transistor, it doesn't cost us anymore because we're making them all at the same time. So the area matters, but if we're able to make them smaller and fit them in the same area of the chip, that doesn't cost us anymore, right? It's the same number of steps we have to do. We wouldn't even know. I mean, if we're running it through, we don't even know that it's taking us an extra burden to add one transistor. So let's go to the board. Let's get a little active here. Go to the board and let's figure out how some of this scaling works and how the numbers, because it's incredible how we've been able to make things small. So let's go to the board and check it out. Okay, does anybody have any idea, for instance, the size of an atom? Small. Pretty small. Well, let's quantify it. How small? Smaller than your pinky. That's not good. Well, no guesses? Come on.
It's like 10 to the negative.
10 to the negative something. Okay. So we'll pick 10 to the negative something. Well, in fact, it's around 10 to the minus 10 meters. 10 to the minus 10 meters. Let me express it in a different unit. It's the exact same thing, but 0.1 nanometers. Nano meaning 10 to the minus 9. So 10 to the minus 10 meters. Okay, so that's pretty small. 0.1 nanometers. Okay. Well, the size of the smallest feature in a transistor is actually 20 nanometers. So that's the kind of, this is the smallest transistor feature. I'll explain what that means. Transistor feature. Okay, how many atoms is that? 200. 200 atoms. But that's 200 atoms. I don't think of things in terms of atoms, right? But that's pretty crazy. talking atoms here. So let me draw a generic transistor here. Okay. So a generic transistor, this might be silicon, as I showed you before, and you introduce some impurities, let's say right here, that makes this conducting. I told you you can change the conductivity a lot. And we introduce some impurities here that make this area conducting. But if we don't apply any bias here, this region is not conducting. So if this is our light switch here, so this is kind of the flipping of the switch here, and this is the wire kind of going through it. So if we don't put any bias here, so this is metal on top of the insulator here. So we put a metal layer, and an insulator keeps electricity from going this way. But if we don't apply any bias here, there's no channel to conduct electricity here. It's not conducting. But if we put a bias here, let's say we put a positive bias here, we attract charge here, and we can change the conductivity of the semiconductor material. And then we get a channel formed here. And now current can form. So that's the idea of how the switch works. That's the idea how a semiconductor switch, a fancy word for it is a transistor. Okay, so that's this word here. So the smallest feature size is this gate length right here. So this distance is about 20 nanometers. So controlling about 200 atoms. Well, that's pretty cool, right? I mean, that's pretty small. Well, the computer chips that you buy that are in your phone, that are ubiquitous in our society, not only do they have this for one transistor, they have this for about 1 billion transistors. So that's 10 to the 9 transistors, okay? So you're getting something atomically engineered across 1 billion devices, okay? So that's a big number. But 20 nanometers, okay, that you might say, Jamie, that's pretty big. 200 atoms, I mean, that's a lot of that. But the insulator here, this insulator thickness that's engineered across all the devices is engineered to about maybe 2 nanometers, approximately around 2 nanometers in size. So how many atoms is that? 20. 20 atoms. This is atomic engineering at this point. And you can't see 2 nanometers. You can't see 20 nanometers. Like, this is very small. We're talking atoms. And so when I hear about atoms in physics and things like that, I always think, oh, that's so distant. Nobody deals with atoms. Well, in fact, all of y'all deal with atoms. You use it every day to do your computation, to do anything you want on a computer. It's all atomically engineered. And the crazy part is it doesn't cost $1 billion, okay? Crazy part is a microprocessor, microchip, they cost how much? About $100. That's reasonable, right? Around $100, okay? And I have a little secret to tell you. The transistors are actually free. So $100 for the entire chip that has 10 to the 9th, 1 billion transistors. So we'll take 100 divided by 10 to the 9th. That equals 10 to the minus 7 dollars per transistor. Now, y'all aren't impressed yet. I'm about to show you how it's free. Okay, so let's write that out. So that's, okay, 1, 2, 3, 4, 5, 6. So that's how much each transistor costs. That's free. I mean, that's free, right? Like, to prove my point that it's free, so how much does gasoline cost? $3.50. Okay, I want somebody that's like $3.51. I just checked on gas buddy. Okay, so we'll say $3.50. Okay, $3.50. Well, it never costs $3.50 if you pay attention. How much does it actually cost?
$3.59.
Yeah. Okay, right. But we kind of ignore that, right? Because that's annoying. And so let's say, okay, well, this is actually, this is $3.51, right? So we round this number. Okay, so if we can round that number, then I can round this number here, and that's 0. So it is fair. So the transistors are really free. They really are so cheap that it's unimaginable that we can get this sort of performance and at a consumer level. Because if you had to pay $1 billion for it, only a couple of people would have it, and it wouldn't be the revolution that it is today. So scaling has enabled these incredible things because as we made them smaller, we're able to put more on the chip. And so let's make these numbers a little more meaningful. Who wants to make a sacrifice for science?
I'll do it.
You'll do it. Okay, I need one of your hairs. I need you to pull a hair from your head. Okay, let's see if you can do it. Okay. Oh, okay, there it is. Okay, whoa. Should have asked the girl so I'd have a little bit more. But you probably can't see the hair unless you're very close, okay? Well, what's the thickness of this hair? Anybody have an idea? 500 nanometers. That's not too bad, but it's much bigger than that.
2,000.
2,000. So let's use a different unit now if we're 2,000.
0.1 millimeters.
So 2,000 nanometers would be 2 microns, 2 micrometers, right? Well, it actually turns out to be around, let's say, 60 microns. So a hair. Let's say a hair. Oh no, I dropped your hair. If I could get one more from somebody, that would be wonderful. Oh. Yeah, I'm serious.
Okay.
This isn't gonna work. Okay, so 60 micrometers. So a micro means 10 to the minus 6. This is 10 to the minus 9. So how many transistors would fit across the width of this hair? 100, a little more. So this is 20 times 10 to the minus 9 meters. That is 60 times 10 to the minus 6 meters.
3,000.
How many?
3,000.
3,000! Yay!
That'll be applause.
Yeah, so that means across the width of this hair, the width, 3,000 transistors. Okay, so let's say we have the width of the hair by the width of the hair. So we have this little box, right? The same. Does that make sense? How many transistors are there? Not 9,000.
90,000?
100.
9 billion.
9 million! So that means if you had this little, you had a box, right? That was the width of the hair by the width of the hair. In that little area, you could put 9 million transistors. 9 million transistors, okay? So these are big numbers. That's why we don't just add numbers on our computers anymore. We can do a lot of things. And so this is the incredible nature of how small things are. But because of this is why we have to build clean rooms and things, because I'll return. I don't want to steal your hair, so I'll just return it. Oh, okay. We'll pretend nobody saw it. But that's the incredible scaling. What incredible scaling has enabled. But that's also why it's obviously very challenging to make it, and that's why we have to build facilities that remove these contaminants, because a single piece of hair, that's going to knock out so many transistors, and just like a single piece of dust. And so that's why we have clean rooms, and I'll talk about it a little bit more in the clean room tour, but yeah. Okay, well, where's Joe? Okay, so what should we do with the bags?